Time. She spent one summer here in Madison working with our group, and so we were very happy to have her during that time. I think we probably ended up learning more from Marta than you did from us, but
I don't think that's true.
and after that, after she graduated with her PhD, she did a postdoc at Stanford, and now is an assistant professor, faculty member at Duke University. So I know she's going to present on some of the work that she has done in the past to give you a sense of the type of things she is working on and thinking about, so I won't say too many details about that. But very happy to have you here, and thanks for presenting.
Thank you so much. Thanks for having me. And thank you all for being here so close to Thanksgiving. So we'll try to keep it fun. So what I'll talk about is urban water planning, and especially in the context of a lot of drivers of change, changing droughts, or changing climate, changing technology, and changing policy. So what you see here, this is a really pretty picture of the city of Santa Barbara in California. And right downtown of Santa Barbara, if you go there, you might see this big white building. This is a desalination plant. And I want to start today's talk telling you a little bit about the story of that desalination plant. So what you see here is a time series of lake volume in the biggest lake that's next to Santa Barbara that Santa Barbara takes most of its water from. And so what you expect to see in California are these sort of oscillations between a few wet years, a few dry years, wet years, dry years. So you see the lake level going up and down, and that's normal. But what happens in the 1980s is quite a few dry years all together, happening one after the other. And so this was essentially a multi-year drought. Santa Barbara, it finds itself in dire condition, they're running out of water, and they decide they want to invest millions of dollars into this perfectly drought-proof technology that is desalination. These plants take a few years to come online. They have to go through permitting and construction. And so the plant was online a few years later, but by then it started to rain again. There was plenty of surface water again. And so desalinated water was really no longer necessary and very expensive and energy intensive to produce. So what the city did was put the plant in standby after only 4 months of operation, shutting it down, decommissioning, put it in standby, and it then was in standby for the next 20 years until the next big drought, when they decided to reoperate the plant. Now the plant had to be retrofitted and modernized, and so they spent, again, millions of dollars on that, and now the plant is up here and operational again. The reason I tell this story is that it really shows how hard it is to plan when you have this climate uncertainty and your oscillations in your water availability. So the city obviously regrets that first decision of building the desal plant, but it's not clear what they did wrong. The city does need an extra source of water when it's dry, but then it becomes immediately oversized when it starts raining again. And so there's a really delicate balance to strike between underspending, underpreparing for extreme events, and exposing your population of the risk of running out of water, but also overspending, straining assets, wasting millions of dollars into something that's probably not needed, and now that money can be reinvested in the community and has to be passed on to users. And so striking that balance is really hard right now, and it will be increasingly in the future. You can interpret this like graphic as precipitation or temperature, but the point is that the mean is shifting, and importantly, the standard deviation is increasing, and so we're going to have less and less of the average, more and more of the extremes. And also we have unprecedented uncertainty in climate and demand. Sometimes you don't even know the direction of that change, if it's increasing or decreasing. So with all this uncertainty, it's really hard to make decisions now on planning water infrastructure that is going to be online for the next decades or so, when we don't know where the system is going to be. And so what some of the researchers in my field have started to do is they've started to look at the decision-making process itself. So the decision-making process that is traditional, or it's the normal way we make decisions right now, is we look at current and our best guess on the projected conditions, we make a decision based upon those conditions, and then we implement that decision. Some retrofitting may be possible in reality, but it's really an afterthought. And the point is, when we make that decision, cost-benefit analysis, optimization, whatever you want, you do so hoping that that's the right decision for the next 20 years or whatever the lifetime of that infrastructure is. And so alternatively, a dynamic decision-making paradigm, instead of making decision, makes decision policies, which are a set of rules on how to make decisions that change and adapt as conditions change. And so we implement today's decisions knowing that we'll be able to adapt and change the decisions in the future, and then we monitor it. We monitor the state of the climate, we monitor the performance of whatever we've implemented, and that feeds back into our decision policy and informs future implementation of that decisions. And so this essentially means formulating the water planning problem as a feedback control problem. And what that might mean in reality is that a static decision-making paradigm might advocate for building a large infrastructure that sort of buffers the uncertainty in the future, and instead, in some cases at least, a dynamic decision-making paradigm might advocate for building smaller modular infrastructure and building up your capacity over time as your needs change. And so with this sort of like framing in mind, I want to tell you, I'll structure the talk into sort of three pieces. The first one, the first thing I want to talk about is sort of how the characteristics of the next drought that a city would face impact their decisions, their optimal decisions, and how much money they invest in drought planning. The second part is going to look at the fact that climate is not the only thing that's changing in the systems. There's a lot of innovation from the technology point of view and policy, and so we're going to include those innovation pathways into the way we make decisions for our systems, and I want to talk about some future directions as well. But starting with the first one, a lot of this research takes place in Santa Barbara, so I want to tell you a couple of words about that system. So Santa Barbara is a city in the central coast of California, and from the point of view of its water system, it's interesting because it's somewhat isolated, because it's sandwiched between the ocean in the south and then a big mountain range in the north. And so over the years, they had to build up a portfolio of water resources that's very diversified. And so they get some of their water from Northern California. This is the State Water Project, SWP, which is essentially water that's moved from rainy Northern California through systems of canal and infrastructure down to the central and the south coast. Like LA gets a lot of this water, right? Then there's one big reservoir and one smaller reservoir. This big reservoir, Kachuma, is what we saw in that first slide, and that's shared with other municipalities. And then there's also some water technology that is installed within the city. So there's desalination and there's some water reuse as well. So multi-scale planning here, right? And so the problem that Santa Barbara is facing is common, and droughts are becoming an increasing problem in the area. And so they want to build up their water portfolio in a way that's resilient to droughts. The way they did it in practice is essentially complying with what is California law, which requires the water utility to plan for a design drought that is a 5-year drought. So Santa Barbara prepared this water division, their urban water management plan, long-term water management plan, where they're essentially trying to figure out if a 5-year drought started tomorrow, if they're prepared for that and they're resilient to that, right? So we got interested in this because this choice of the 5-year design droughts is somewhat arbitrary. We don't know that the next drought is going to be a 5-year drought. We had longer than that droughts in the past. And also, California is not really prescribing any intensity of the drought. That's really left up to the utility. And so our question was, is there a difference if we plan for short and intense droughts versus long and mild droughts or frequent droughts? Meaning, do the drought mitigation measures that we want to implement in this case, are they the same for these different types of droughts, or is there some sort of correlation between the attributes of the drought we're planning for our design drought and the interventions that we should deploy? And also, what are we monitoring? If you remember that cycle there, what information should we monitor? Is it storage? Is it some sort of like drought index? What are the space and time aggregations that we're interested in? And in other words, how do all these sort of elements interconnect? So this is our question. We came up with some sort of like framework to investigate that. We call it DRIP. And this essentially has three main blocks. In the middle here is a model of the water system. This is simplified, obviously. You've already seen Santa Barbara is much more complicated than this. But you essentially have a city that has a water demand, and it's trying to satisfy that water demand using a mix of like surface water and also some technology and water supply. And then that surface water is forced with scenarios of droughts. So here we're going to test our different types of design droughts to see how the city sort of is affected to these different droughts. And up here, we have all the things that the decision makers in Santa Barbara can implement, all the technology and policy options they can implement to mitigate those droughts that come from here. So here's where we're going to like try to like implement that loop where the hydrology force, sort of the decisions are taken as a function of the hydrology within the systems, right? And we're gonna start, like now I'm gonna open those boxes one by one to see how we've implemented this. We're gonna start with how we generate our drought scenario. And we came up with a synthetic drought scenario generator. We called it FIND for frequency, intensity, and duration. And so in this scenario generator, the user is able to determine the types of droughts that they want to generate, so the duration, intensity, and frequency. And so basically the way it works is that there's a randomized extraction of a sort of pseudo-random streamflow time series that extracts from the distribution of the data that's observed in an area. And then based on this sort of randomized extraction, we compute some objectives. We want to preserve the time autocorrelation. We want to preserve the wet periods and only change the dry periods. And then here we're going to calculate the frequency, the intensity, and the duration of the droughts that we generate. And we calculate that on drought index, not directly on the stream flow. And then the way the optimization works is that we're going to pick out a piece of this stream flow, and we're going to substitute it with a different random extraction, and we're going to calculate the indicators for this swapped time series, and we're going to select out of these two, we're going to select the time series that is performing better across our indicators, and that becomes our new parent. And then we go through this sort of iteration of swapping a piece of the time series for 1,000,000 times until we get to the objectives that we want, so those characteristics that we want. I put this on GitHub, and this is like the one code that I really try to look nice and got a lot of comments on, so if you want to use it, please do. But okay, so this is how these drought scenarios look like. They're shown on the drought index, so positive for wetter than average, negative for drier than average. And we're able to create synthetic scenarios where we can control the intensity and duration of the frequency. And so these are preserving, historical droughts are preserving these characteristics that we've seen historically for the city. And then we can create short and intense drought, long and mild drought. So here, the red area under the curve is the same, but it's just distributed differently. And then we can create frequent droughts as well. And so those will force the system. And then if we open the box of the technology and policy options, here I relied on models of the treatment train technology that were available from our partners in NAUI, which are essentially a technology hub. And I have all these models, and they're able to model potable, non-potable reuse, seawater desalination. And these are deployed either centralized plants that serve the entire city or decentralized plants that serve a neighborhood at a time. And we're also considering conservation, mandated conservation as another option for the water planners. And so from these models, we're able to get capital costs, operational costs, a bunch of things. I can visualize here basically a levelized cost of water, which is the unit cost of producing 1 unit of water from each of these. And we see what we would expect. Centralized is a little cheaper than decentralized because it benefits from economy of scale. And then non-potable reuse is cheaper than potable because it requires less treatment, right? And cost is an important factor, but it's definitely not the only attribute of that technology that determines whether it's a good way to respond to droughts or not. And so in this messy spider plot, what I'm trying to show is, so this is a bullseye plot. If we had a perfect technology, this would be a small pentagon right in the middle. We don't have a perfect technology. We have a lot of trade-offs between this technology. Without going into too many details, if we look at this dark red and dark green and dark red, what we see is that decentralized in green has a higher LCOW, a higher cost, but then it's more scalable. It takes less time to deploy, which might be actually really important when you're in a drought. It cuts down on distribution energy as well, but has less capacity. So essentially, you have trade-offs, and the point of this slide is just to show there's no obvious technology to deploy in case of drought. There might be better ones depending on sort of the condition area. So this is why we formulate a whole optimization problem to determine what to deploy, what technology to deploy in response to what climate. And this is how we formulate our optimization problem. We connect indicators of the state of the system to the action, the drought mitigation actions to take, and this connection is done through essentially decision trees. So decision trees are going to tell us when our indicator falls below a certain threshold, this is the action that you take. Our indicators are indicators of the state of the climate, the hydrology, the technology, at different time scales. We have a lot of options there. And then the actions are the technology options that we just saw. And then there's an optimization here that optimizes essentially everything about that tree, the structure of the tree, the type of indicators, the thresholds, and the action. And then finally we get to some results. This is how our optimal deployment looks like. So you have the drought scenario here at the top. This is a historical one. And then you have, like here at the bottom, how the reservoir storage changes in response to that drought scenario. And in the middle are optimal deployment capacity decisions, right? And so here we're deploying decentralized capacity for most of the time horizon, and then, centralized capacity for most of the time horizon. And decentralized capacity comes online only during droughts as the reservoir storage depletes. And so this is just one realization, but obviously we sort of train our policies across many realizations of these droughts. And what we can see is that when we change a drought scenario, the optimal decisions change a lot as well. And so if you're trying to respond to long amount droughts, you need a lot less capacity in general because the storage buffers most of your drought. And so you need just a little amount of centralized capacity to come online towards the end of the drought. For short and intense droughts, it's the opposite. You need a lot of baseline production to be online at all times, because once a drought hits, the storage depletes really quickly. And then you also need to add some decentralized on top of it. And for frequent, it kind of looks like the historical droughts, but the difference is that you need a lot more decentralized when your droughts happen right after the other and they compound, and the storage doesn't have time to replenish. So again, these are single realizations. We can look at the results a little more in aggregate with something like this. So here each bar is a different type of drought. The intensity of the orange is proportional to the amount of installed capacity you have. And so basically what this tells you is that you need most capacity in short and intense droughts, the least amount of capacity in long amount droughts. And we can also optimize for all the droughts altogether. And this somewhat looks like the short and intense. Another thing that we thought was nice is that our optimization for historical droughts requires an amount of capacity installed that is very similar to what where Santa Barbara is right now. So that kind of a hand-waving, let's say, validation of our decisions, right? But not only, so basically to get us back to where we started, like if you're using each of these as your design droughts, you wouldn't make a lot of different decisions depending on what your design drought is, right? But not only the total install capacity that you want to deploy changes with the different types of droughts, also the type of capacity that you deploy. So here I'm showing the percentage of the portfolio of capacity deployed that comes from decentralized. And that seems to be highest for short and intense and frequent droughts, right? Not only that, but also the type of information that you use to trigger your decisions also changes. So for instance, historical droughts are generally, responses to historical droughts are generally triggered by drought indices. Responses to long ML droughts are triggered by reservoir storage going down. So this is information that's a little more reliable in terms of droughts, but it also has a lot more inertia. And so that works if your drought comes online really slowly, and then you can respond to the storage. Otherwise, you can't. So for instance, for short and intense drought, you're deploying more technology when you don't have enough technology. This is what it says. And that just means that you don't have time to respond to the climate. That's too quick. And so you're just building more when you don't have enough. And then planning for all droughts altogether looks like planning for short and intense droughts. This all comes together in determining very different costs of planning for these different drought types. Short and intense, again, is the most costly. Long ML is the least costly. And planning for all droughts is just the same as planning for short and intense. And with this last slide for this first part, we can have a sense of like what is the risk and regret of planning for this of choosing different design droughts. So in this heat maps, here we have the drought that we're planning for, and in the columns we have the drought that happens. And so, and the colors is a deficit. So for instance, this square here is the deficit of a policy that's optimized for historical, but then a short and intense drought happens. And so what happens here, or what we see here, is that probably not a good idea to plan for long and mild droughts because you end up with deficit in all the other drought types. Short and intense droughts are the most challenging for the system because they create deficit in all the other types of droughts. If you plan for short and intense though, then you're robust across all of the other drought types. So this would be a good design drought because it allows, even if the drought that actually happens is different, then you're still robust to all the other counts. And it's the same as planning for all droughts altogether. So if you're really interested in robustness, this is a good idea, but we've seen in our previous slide, this is the costliest drought to plan for, right? So then this shows kind of the extra cost that you're spending, the money you're wasting, if you plan for like pure robustness and then a different type of drought happens. And so for instance, if you plan for short and intense and a long dry and mild drought happens, you're spending 3.5 times the money that you would actually need. So a few take-home messages here. The design drought that you pick is really heavily influences your planning decisions. So, when California sets their 5-year design drought, there's a lot that goes into then essentially influencing the decisions that are actually taken at a system. When California prescribes 5 years of design droughts, duration doesn't seem to be the most important drought driver in the city of Santa Barbara, at least. Intensity is much more important than duration, and so that part shouldn't be left up to the utility, really. And then the other thing, more from the climate perspective, is I feel like there's a lot of research in predicting the onset of the next drought, like when it's going to happen. What I'm showing here is that there's actually a lot of value in predicting exactly the attributes of this drought, not only when it's happening, but also the duration and the intensity of the drought, because that's what it's impacting our decisions a lot. On to the second part of the talk. Take a water break. In this part, I want to discuss the fact that a lot of this research in this field looks at climate uncertainty a lot, but if you're planning with like 50, 100-year horizons, climate is not the only thing that's changing in the systems. There's a lot of changes that happen in technology. There's things like desalination and reuse are likely to become more efficient, more usable. Policy's changing a lot. We have new funding opportunities, new water markets, and we have all the ways that policy regulates technology as well. And this happens on top of climate change. And so these boundary conditions are changing all the time and sort of all together, and so we should consider them all together. And so this is a way of doing that. This looks exactly like the other framework that I've shown, except I divided up the technology and the policy into two different blocks, and I'm highlighting the drivers of change and innovation when it comes to technology and policy that we're gonna play with. And so what I'm gonna do is I'm gonna solve the same problem, but I'm gonna play with the knobs of the innovation, and I'm gonna change some drivers at the same time and see how that affects our optimal decisions and our costs. And I think this is important for two things. One is because it informs water planners on how to yield the advantage of innovation, but it's also informing innovation itself. So when you're planning for climate uncertainty, you don't have a way of going back and like influence the climate, right? But when you're planning for innovation and technology, you do have a way of going back to the innovation hubs and say, these are the technology innovation trajectories that will yield the best benefits at the system level. And so this is what we're going to try to do, identify the high impact innovation targets for this. And so I'm going to show only one results for this when we're playing with the technology costs. And we're going to play with levelized cost of water and capex ratio. So levelized cost of water, COW, I've already described as the unit cost of producing 1 unit of water. And that accounts for the capital cost of deploying that technology initially, and then the operational cost of operating it over time. And so then the capex ratio is the fraction of that unit cost that comes from capital cost. So you would have up here, high capex, so OpEx technology, expensive to bring online, cheap to operate, and then down here, cheap to bring online, expensive to operate. And so at the technology level, what you're interested in is just the LCOW, right? It doesn't matter where the cost is coming from, but it's just you're looking at only the unit cost. And so your ISO cost curves are vertical. But what we want to do now is we're going to solve the planning problem for all these sort of combination of these costs for the system. And what we see is that at the system level, these ISO cost lines are not vertical anymore, and that means the LCOW is still an important factor, but now capex ratio becomes important as well. So what you're seeing here is the cost, we sort of play with the cost of centralized technology and decentralized technology one at a time. And then the 0% is zero difference with respect to baseline. Blues are cost saving with respect to baseline, and then reds are more expensive than baseline. And so to understand these plots here, we should look at how the baseline looks like. Essentially, the optimal planning here uses both centralized and decentralized technology, but it uses it very differently. So centralized is brought online once and then operated steadily for the remaining of the time horizon. And instead, decentralized technology is brought online during each drought and then decommissioned right afterwards. And so for centralized technology, most of the costs come from operating the technology for a long time. And so the most impactful innovation tries to increase the capex ratio to make operation cheaper, essentially. And the opposite is true in decentralized, where most of the costs come from the capital costs of building up this technology all the time, and then operations are very short. And so what you're trying to do is to reduce the capex ratio so that bringing online that technology is cheap, and then it's fine if operating it is expensive because you're operating only for the time you need it, and then you're decommissioning it right afterwards. So the way then this feeds back into informing essentially innovation targets is, let's say you have a new innovation, let's say a new material, these come up all the time, like a tweak of an old material, something like that, that lowers LCOW by being expensive to implement, but then enhancing efficiency. This would be going up in the CapEx ratio. You have to implement it at cost initially, and then it reduces the cost of operating it. So this would be a good innovation to implement in a centralized plant, because you're going up here to a cost reduction, but it wouldn't be a good idea to implement in a decentralized plant that you're operating more intermittently. And so this is how it's sort of like parsing out what are the good innovation trajectories, what are the good innovation that can go into this plant. We also play with a lot of other levers of innovation. I'm not going to talk about it. One thing I'll mention is that with our innovation in time, where we're essentially playing with the deployment time of technology, we were able to write a comment on to the State Water Resources Control Board in California that is essentially evaluating the streamlining of desalination permitting, so making desalination quicker to deploy, and we're able to sort of quantify what is the advantage of that at the system level in terms of like saved costs. All right, so a couple of take-home messages here. The idea, so at the technology hub level, at the technology innovation level, a lot of the times you're just focusing on SCW. And what we want to show is that actually focusing on different levers of innovations, such as CapEx ratio diversification or quicker deployment, can actually yield a lot better savings at the system level than just only focusing on SCW. And then with that, you can sort of identify these high impact innovation pathways that play with these different type of innovation. The other sort of thing, I'm not going to go into too many details, but you can imagine that at the system level, some innovation will be more likely than other. And so testing a lot of innovation pathways can also allow you to identify many innovation pathways that can lead you to a cost reduction, so that some will be more feasible and less feasible at the system level, and you can sort of let your decision maker figure out which ones are the better one for your system. For that, I want to thank, this is most of the work that I did during my postdoc, so I want to thank my advisors, my postdoc advisors, Sarah and Megan at Stanford, and also the Technology Hub that funded this research at now. The last thing I want to spend a little bit of time on is like the future direction, how we're going to build onto this research. And the first comment I want to make is a lot of research in my field, mine included, is very case specific. Like we pick a case study. For us with Santa Barbara, we collect all our data, we make all our models, we run all our optimization, and then we have our results. But this set of results is only specific to Santa Barbara, and we don't know necessarily how much they're going to scale up with two different municipalities, right? Because they're really sort of depending on the specific recipe of attributes that Santa Barbara has, like their storage to demand ratio, their hydrology, their demands, etc. So if you're sort of abstracting this a little bit and you think of a hyperspace where each axis is a different attribute, Santa Barbara will be somewhere in that attribute space, and their optimal planning strategy will be something that we call orange, right? And so if you move slightly into this attribute space and you pick out a different municipality, you might have a different optimal planning strategy. And so if you, one thing you can try to do is you solve a lot of these different problems across this attribute space. And the reason why you want to do that is you can sort of try to understand how the planning strategies change as a function of these attributes to determine a little bit like what is it about Santa Barbara that determines that that's the optimal solution. And sort of that helps you generalize a little bit our results beyond just the case study. And we're getting to some of it with this, as I'm collaborating with Marie Gross, Alvarez, Peter Brewer, of course, and Marta Zaniolo, who developed this sort of database of utilities in California. It's called CARDS. And the database is collecting essentially water supply data, demand data, something about precipitation, the climate, and sort of droughts. And so what we're trying to do is essentially clustering utilities into these sets based on their attributes, for instance, how much their water comes from groundwater, surface water, or a mix, and then what is their size, etc. And we're going to solve a few different utility problems in this space to start of coming up with kind of policy relevant guidelines for a little bit broader around the state. Another thing that this helps us do is sort of pairing cards with, pairing my optimal planning with cards is that our demand assumptions are going to be refined a little bit because they have sort of like dynamic demand assumptions in there. And this is really important because getting the demand just right is really important to determine utility revenue. Because utility revenue is essentially basically through water bills, right? And so we need to know what's the demand to determine their revenue. And one thing that came up over and over in my results that was kind of surprising to me for Santa Barbara is that conservation, asking the population to conserve water, was really expensive for the utility in terms of loss revenue. And this is sort of intuitive, but I want to explain exactly why. So a water bill generally looks like that. You have a small fixed cost, and then your water use, or your cost marginally increases for water use, right? And so the reason why the water bill looks like this is that it makes like water for sustenance affordable. So if you use less water, it's affordable, and then you want to discourage excessive use and waste up here, right? So this is great, and this is sort of like what the revenue looks like for the utility, but this is not what costs look like for the utilities. Utilities tend to have very high fixed cost and very low marginal cost. And so as you normalize for all you aggregate for all the consumers, like everything works well when your like demand on average is sort of around here. But then when you have a demand reduction, your revenue deficit can be really high when these curves are very different from each other, right? And so we're going to add another objective to rate setting here, which is ensuring that the utility has some sort of financial stability to this water demand that fluctuates a lot. And so if we formulate this as a multi-objective problem, where each utility is a point essentially in this like three-way optimization problem, the idea with this research is to try to like first kind of develop metrics and understand how does different utilities map onto this these three sort of indicators or objectives of rate setting, and then from there try to see if there are some sort of like trends in time that are observable. There is some sort of anecdotal evidence that after a big drought, utilities tend to raise their fixed cost, and that means essentially moving away from affordability and towards financial stability, closing the gap between these two curves. And then the third and like the larger idea here is to try to like redesign our optimization problem to optimize for supply and for rate setting altogether and see what we get. And I think what we may get is that utilities may prefer to essentially deploy drought mitigation measures that have lower fixed costs and higher marginal costs to try to close the gap between these two curves. Because if these two curves are perfectly parallel, then conservation is free, right? If your marginal cost and revenue are exactly the same, it doesn't matter where you are. And so this is sort of like the proof, we're going to try to like develop a proof of concept for this. this is all I wanted to tell you. I'm gonna just like leave you with a couple of thoughts. Hopefully convince you that urban water planning is really hard and it's complicated by all these changes that are happening in the system all at the same time. This idea of like recursive decisions or dynamic decisions can help mitigate a little bit of that because you can sort of react to the system as it's changing. I see an opportunity and a challenge. The opportunity comes from all the exponential advances that we have in data and data gathering technique and forecasting techniques that can help us make our decisions a lot smarter and our early warning systems a lot smarter than they were. The challenge here is that what we're advocating for is decisions that are taken at a much higher frequency than we currently are able to make. And so our governance structure is not really set up to make decisions every few months. We have a plan that comes out every 5 years or 10 years, right? And so what we're advocating for is a lot more frequency in that. And with that, I thank you very much for your attention. You looked very engaged my whole talk, so I really appreciate that.
All right. Thank you, Marta. Very nice presentation. So if there are questions, we can take any of those.
We do have a question online that I could
Okay.
start with.
Sure.
Did you consider population variation occurring in the 5-year planning for drought?
That's a good question. Okay. No, we had our demand assumptions that were constant. Okay, so the way that population would factor into this is how it would change our demand, right? Our demand assumptions were constant because we were hoping to sort of see changes in demand through the utility, essentially requesting the population to conserve water. And we didn't really see that. The reason I'm making a distinction between demand and population is that those two don't necessarily go together in a way that you would think. So actually, California has dealt with this. I might have a slide about this, but it's okay. Population in Southern California has steadily gone up. And even then, total demand has gone down. And the reason is that efficiency in appliances has gone up a lot. People have just changed their behaviors. They're not irrigating their lawn as much. They're changing the type of lawn they have. And so looking at population projections are easy to get, but they're not a good indicator of demand necessarily because you have all these changes that happen in the system simultaneously. It's more about trying to predict demand. And there's a history of doing that really badly, or at least for Southern California, because you would think it would follow population and it would go up, but it's steadily gone down. And so, yeah, so it's actually a lot, very, very hard to do that.
So first, a clarification question. When you showed that the short duration intense droughts were the most expensive kind of.
Yeah.
Would you call those, where does flash drought fit into your definition of short and intense?
Yeah, you would call it that. I don't think so. What I've seen define flash droughts in the literature is like maybe a seasonal drought. That wouldn't even be a thing in California because what you would see, like the climate in California, like it's absolutely normal that it doesn't rain for a whole year, right? It's definitely normal that it doesn't rain for a season. A lot of your precipitation comes in like concentrated events during the winter. So like flash drought would still be something that happens over the course of like 2-3 years for it to matter for this specific like Mediterranean climate. So I guess it would be a flash drought for the area, but it would be very different from like.
Well, it's more like how rapidly the onset is.
Yeah, exactly. So it's about rapid onset, but like when you have, it's an interesting thing to think about droughts in California because the way I think about it is like lack of wet extremes that causes a drought rather than the dry extreme. It's like you're missing your stores.
And then my second question is, so you talked a little bit about it with your cards work, but how would you design your optimization when you have more groundwater use. And so,
Yeah.
to me, it seems like then the even long duration, less intense droughts might have a more significant role. Have you thought
Yeah.
about that?
Yeah, definitely. I think, right, I was trying to be careful when I was presenting my results and always saying like, this is true for Santa Barbara. Exactly, because when you have access to a lot more water market, so Santa Barbara was really nice because it's somewhat isolated, but once you have access to more water market, and once you have access to this long-term storage, like groundwater, your results may change as a function of like the things you can do, like the job mitigation measures that you can take also may change a lot. So I think you're absolutely right. I would think like the framing of the problem would stand, although it's a lot harder to model groundwater basin than it is to model lake. So, well, you have to figure out some of those aspects, but the framing would stand, but then the results would change in that, yes, if you have a long-term drought, you might rely on your groundwater a bunch, and that might get you through that drought, but then if like it's long enough, or if you have if you don't have time to replenish that basin in between droughts, then your second drought is what's going to hit, right? So you have a lot more of this sort of like time dimension to it, that it's going to take a lot more importance. I think right now in California there's like a recent initiative that's called SIGMA, Sustainable Groundwater Management, I would imagine. So now they have a lot more regulation in the way that they can use groundwater and the way they have to replenish the groundwater basin. So there's sort of a little more constraint in what they actually can do as utilities and farmers, etc. But that doesn't you still have a lot of room in how you manage the resources.
I'll ask one if I might then. So kind of related to the different drought characterizations that you're bidding them into. And obviously you're a little bit inhibited by the length of the record. Have you looked at paleo data at all, or other types of records that could really extend both to see more of these different types of droughts and or if the frequency of them is changing, et cetera?
Yes. More recently, I have looked at some sort of papers doing that. This is not included in this research. Like this research that didn't look at that. But it is really interesting. It's like maybe not available for like Santa Barbara specifically, obviously, right? It would be more of a regional analysis. It would help you, looking at paleo data essentially helps you determining what a historical drought really is, right? Which is not the past two droughts, it's like going back to the mega drought of the Renaissance, right? And things like that. And so it helps you determine kind of the variability that you have, even in historical conditions. Let's say that the type of droughts that I was trying to design for that first work weren't necessarily like realistic drought, but it's more sort of like about how our decisions are like drastically changing when we change the drought we're planning for, and what are we most exposed to, right? So it's that intensity, at least for Santa Barbara, that it's really the vulnerability of the system. And so once you know what your system is vulnerable to, then you can take steps to try to build in robustness for that.
Yeah.
And so in a way, sort of like that's what we were going for, rather than specifically like accurately determining what a historical drought is.
Yeah, that's fair. So if you ended up tailoring this to a specific community, one could do that as well.
Right.
So just one follow-on question, and this same idea with these drought types and bringing it to the conservation question at the end. I'll be guilty of not thinking about this enough, but whether a utility decides to promote conservation or not, and I get the cost to the utility of doing that, that would also be contingent on the type of drought too, right? So for some kind of drought, short mild, I don't know if that was even one of your types. Conservation might be the right approach there, right? Because they don't want to
Yeah.
build more capacity,
Yeah.
and they can eat that cost, but it still
Yeah.
works out in the long run versus these more intense droughts where the
Yeah.
capacity is the only way to get through it.
Yeah, and there's a lot of like, modeling choices that go in here that I haven't like described fully. The tricky thing with conservation is that you would, as a utility, what you would want to do is to enact conservation, and then once you have enough water, forget about it, don't implement it anymore, right? So that our
Yeah.
revenue can keep going up. But this is not what the population does. There's a long rebound after you enact your conservation mandate, and so your water use doesn't bounce back as you want it to. It like stays lower for much longer. So if you want to respond to a short and mild drought with that, you still see the effects of it much longer after the drought happened. And our assumptions for that, in the grand scheme of things, were like not really favorable for conservation, because essentially our assumptions said there's ways you can model this will be based on a different sort of work on dynamic demand assumptions for Ocean County, which is very similar to Santa Barbara, so both very close to LA. That said that your demand goes up, like your conservation halves. So after 8 years, your demand is rebound from half, right? So that's a really long time of foregoing revenue, essentially. And so now for other communities, the rebounds are much quicker than you get your half-life around like 2 or 3 years. So maybe like that's where playing with those assumptions we'll see conservation used a lot more. We didn't do a ton of sensitivity on that. In hindsight, we probably should have. But yeah, we based off of like the closest sort of community that we could find, and that's a really long rebound time. Yeah.
Thanks.
Yeah.
Any other questions?
I was just curious, is there anything, it's similar to how does a city adapt to stream increase it with flood mitigation? Like, is there this kind of approach being used, or how do you, right here in Madison, they're just building like crazy,
Yeah.
increasing storm drainage, and everybody has to keep their rainwater on the property when they build a new building. So it's kind of the same thing, when you're trying to predict something extreme.
Yeah, and sort of like build up your capacity to it. I would think so.
Or you're considering all of these different parameters to make the best choice, and for the different time scales.
Yeah, I think like there's a very similar thinking that would be applied to preparing for floods. Obviously, like you would need to tweak the timescales that you're thinking about, and like obviously the measures, like the decisions that you can take to think about that. But I would think this sort of like idea of like thinking recursively of your infrastructure is a good way of thinking about this. I think as I'm thinking of flood now, and you also have a lot of sort of like levee effect to flood that this sort of recursive decisions might help you with. So essentially, if you build a big seawall, or in this case, like lake wall, to protect your city from flooding, then what you're encouraging is a lot more new builds right next to the seawall, because now you're protected, right? But then as your next flood goes right above your seawall, you have a lot more destruction than you had before you even built a seawall. So this is the levee effect that I'm describing. If you're not taking these recursive decisions, you might have a lot more of this sort of like unintended levee effect. Instead, if you're like taking recursive decisions that are sort of based on the current state of your systems, you might see these effects a little better, and might be sort of trying to minimize the unintended consequences of these effects. So yes, I think there will be a lot of like tweaks to do to the framework, but like the idea of like observing your systems and sort of like trying to see and adapt to the changes is definitely applicable to flooding as well.
Any other questions?